Okay, þá er ég byrjað að taka upp. Welcome. We're going to do an electronics design lecture now, and just to begin with, I wanted to take a look at the Arduino. Many of you might know the Arduino, some of you might not know the Arduino, but it's a nice kind of starting point because an Arduino encapsulates most of the things that we're going to be working with in this module. And an Arduino is basically a few things. It's the brain. It's the chip that controls the logic gates in the circuit. It has 2, even 3 power input devices. It's the USB, it's a barrel jack, and then you have a wired connection. An Arduino also has an FTDI chip, so you can communicate with it, and I'll explain that later. And then these chips, these pin headers are used for to program the initial stages of the brains, and that is the ISP that we made a couple of weeks ago. So you can actually use the Fab ISP to program the Arduino, but you can also use the so-called FTDI interface, or UDPI. The new chips, we got this cycle, we got new chips, we got new tiny microcontrollers, and they don't specifically need an ISP initially to be used. That's the main difference. It comes with an internal bootloader. That's the biggest difference between the Arduino. Between the anti-tinies we had before this and the ones we have now. So this is the Arduino, and an Arduino has digital inputs and outputs, and then analog input-outputs, and then it has some power controls, and we can talk about that later. The Arduino also has an internal clock, or a crystal, which is over here. And then it has some power regulators. But it looks like, a bit of a complex device, but we'll go through it step by step and see how it actually works. What are the core principles that we're going to be using. Now, before I go into the design part of this, I wanted to show you a few examples of Hello World boards that have been made in the past. So here we have a very, very basic Hello World board. It consists of, let's see, the focus. There we go. Somewhere. It consists of the brains. It's the same brain as in the Arduino, just a much smaller form factor. It has a clock. This is a crystal, or a resonator, as it's called. And then it has programmable pin headers, the same as on the ISP. This one specifically has a USB port, which can be used to power the board, but for nothing else. And then it has some capacitors, resistors, capacitors, an LED, and a button. If we take a look at it even more tinier, here's a different board, and this one specifically has a 6-pin header, and this pin header can be used to program the board through a UDPI or an FTDI cable. We have this cable, and I strongly recommend having this cable because it makes for a much easier programming afterwards, but it also makes for power, and it also, so you can use this for power, and then you can use it to communicate with the board on the go. You can communicate with it while it's working. You can't do that through the ISP specifically. This board also has a button, as you can see over here. It has this pin header, this 6-pin header, as you can see over here. And then it has a LED, which is just the light with a resistor, and then the internal regulator. And you can see these are just traces, and they connect different parts of this board together. So while we're going through this, actually, I'll configure the video again. So while we're going through this, the board doesn't need many parts to work. If we go into the Fab Academy webpage, for example, we can see that some of the example boards that we can find on this webpage, on the Fab Academy webpage, some of the sample boards only contain the brain, the microchip, a capacitor, an FTDI pin header, and then a double pin header for UDPI connection. So this is the most basic Arduino board you could ever make. It doesn't really do anything except take inputs from a computer and then transport it to another computer. So you can communicate to the chip, and then you can make the chip communicate to another computer or another board. The assignment for this week is to make a chip, such as this one, but add a LED to it, and then also a button, and then program it just to do something very, very basic. That is the core principle of this week's assignment. When we're designing for something specific, it's best to actually go and find the datasheet for that board. And the datasheet, while maybe quite vast and it has a lot of information that you don't really need to understand, at the very moment at least, in parts of the datasheet you can find exactly what each pin does. And in this case, pin number 2 is a so-called PA6, and then you have PA0, which is the reset or UDPI connection input. We have the clock, and that's about it. This little chip, this tiny 412, has only about 5 functional input-output gates. We can, if we want to use this, for example, which is a little bit bigger one, this one has almost 10 functional chips. If we can find the. So to begin with, we want to go and we want to find the schematic. We want to find the datasheet for the programmer, for the microcontroller unit that we want to use. So I'll just leave this here, and I recommend the ones that you are going to be using. Either you're going to be using the new ones, since we just got them recently, or you might be using the old ones, and then you'll need a programmer with it, which should be found in any lab anyway. So that should be fine. So yeah, just figure out the chip that you want to use, and then just briefly go over the schematic and see what you want to find out of it. Now, once you've found the chip that you want to use, you want to use a Pcb Design Software, such as Eagle, which I'm going to be using now, but you can also use KiCad, or you can use any other ones that you find more comfortable. And they all have the very same principles. They all work really similarly. The biggest difference, and the difference in ideology, is that KiCad is open source and free, and will always be so. Eagle is proprietary, but it can be used in the same way as Fusion 360. That is, you can use them interchangeably. You'll have to pay to get some of the more professional features of Eagle, which you might be able to find in KiCad, such as multi-layer boards and stuff like that. but for practicing and just figuring things out, it's fine. The first thing that we need to do when we download Eagle is we need to download the libraries. We need to download a library for the Fab Lab inventory. And we can do that by going into the Fab Academy webpage, and in the Fab Academy we have libraries, and under libraries we get over here. So this is what I meant to do. We get to here, and the communities that support each program, the communities for Eagle, for example, they make the libraries the vendors actually, DigiKey and such, they make libraries for both Eagle and KiCad. So you can both have the three-dimensional designs, you can have the foot paths of the components, you can have most of the things that you need. So if you go into Eagle, you both have the library, that's the physical library of Eagle, so we can find all the components that we should have in our labs. And we also have something called design rules. So design rules are basically the size of the mill bits that we're going to be using, the speeds, and all the rest. So it's good to have the design rules ready. You can download them. Once you have them downloaded, you can pop into the control panel. Sorry. You can pop into the control panel. You can find, let's see. Just download them. You open up the folder, and then you can basically just drag and drop. It's just a drag and drop thing. You don't need to go through any hoops to import this. You just drag it and drop it, and then the green dots here, they represent if you want to turn them on or turn them off. So now I have both the Eagle new Fab library. I also have the old Fab Lab library that I had from before it got updated. So opening up the schematic, we'll be able to have this canvas here. This canvas is how we draw and how we connect the different components together. So over here, we just add a part. We go into the Eagle library. We find under the UC, and then we have the microcontroller unit. And I'm just going to use the foot path for the Tiny 44. The Tiny 30, the new Tiny, it's called, the new Tiny is called, sorry, the new Tiny is called Tiny 3216. It has this, I'm pretty sure it has the same foot paths as the Tiny 44, but I'm not 100% sure, but that's supported by that it doesn't have a new, there is no Tiny 3216. It's just a Tiny 244 SSU, which has a SOIC 14 footprint, so we'll be able to use that, and that's fine. Once we've placed this one, it's nice to find all the other components that we want to use. So for example, I do want to use the FTDI SMD header, and I'm going to place that over here. Then I need some capacitors, some unpolarized capacitors, and I want to have a C1206 foot path for it. Sometimes we can have other foot paths, but this one is the most standard one that we have. So right click, I can rotate it, and then I can just place it where I want it. I also want a LED, such as the one that we want to use. I also want it to be 1206. I can place that over here. With the LED, I want a resistor. Resistor. I want a 1206 resistor. I can either place that before or after, it doesn't matter. And then I want a button. Then I want a button. Okay, can't find the button, but I'll put the resonator. Either we have a crystal or we have a resonator. Some people have both. It doesn't. It's good. Maybe it's under slide switch. This is slide switch. Ah, there we go. There we go. Yeah, yeah. This one. Here we go. So we have a switch and LED resistor, and I want. Yeah, okay, so this is essentially what we need. We don't really need anything else. We might want to add a different power input. We might want to add a programming. So if we want to use the ISP, we can put the 6-pin headers. But for what we need, for this specific assignment, we don't need anything else but this. Now, once we've placed our... Yeah? Yeah. What is different in the new library? I am using the new library now. Yes, I'm using the new library now. In the new library, I couldn't find the new MCUs. I couldn't find the new microcontroller units, but I did do yes, I'm using the footpaths of the 44. That doesn't mean that I'm using the 44 as such. The new 3616 MCU is no different than the 44, except it has more memory, it's faster, and it doesn't need a bootloader. It's the same size. But I'm fairly certain. I'm not 100% sure. I didn't have time to find that out 100%. So it's good that you do a little research before you get into it, and I'll do some research after this lecture as well. But I'm 95% sure that you're going to be fine doing it this way. Moving on. Now we want to connect the components together. We want to so we want to use the microcontroller and have it do some stuff. So in this section over here, this is the functionality of the MCU. This is what it does. So it has a bunch of pins, such as the Arduino. So these pins over here represent roughly the same as these ports on the Arduino, except on the Arduino they're placed very, very neatly and very accessibly, whereas in here we're going to have to connect them through a PCB, and we're going to have to definitely we're going to have to connect them, and they can't be changed afterwards. So I can say, for example, okay, so now we get to a part that I need to explain probably. So why do we have a capacitor over here? If we switch back to my desk cam, so we can see on this board over here that we have a capacitor. So over here we have a capacitor between the ground and between the input voltage. So why does that happen? And let me briefly explain. So in this tiny device over here, we have millions of tiny transistors. transistors are basically very small solid-state buttons. They just work as on-off switches. They just work as on-off switches. So when these switches are turning on and off, like 1 million times per second, the power that is coming in, it needs to have a little siphon. So it's going into the box, and in the box there's a processing going on, and the process requires different amounts of current. It requires different amounts of electrons at any given time. So in order to not, because the electrons at this tiny level, they have a little momentum. They have some push, you know. So this capacitor, the capacitor that is leading from the voltage in to ground, the capacitor is basically just working as a little siphon. It is a filter. It enables a very current flow of electrons going through, and then it takes the excess electrons that are not needed by the microcontroller unit, and it just throws them out. They're not needed. If we didn't have this capacitor here, we might break the microcontroller unit, because the electrons might push the transistors, and then eventually you might have a break, you might have a fault. In RGB LEDs, for example, so red, green, blue LEDs that you can change on the fly. You can change them from red or green or blue or anything in between. Varying light sources require different currents. So you might go somewhere between millivolts to fractions of millivolts up to millivolts. Milliamperes. I mean, so that's why we have capacitors in between the ground and the power and the voltage in. That's to filter out all the hectic power input. It's also it's both to protect the component that we're placing, and it's also to protect the power supply, the component that gives us power to the circuitry. Any questions related to that specifically? Maybe not. So either way, that's why we have the capacitor. So if we go on, we can use equal to we can give these ports specifically, we can give them names. So either we can connect them straight to the component itself, like so, or we can be a bit cheeky and we can just place a node, like so. We can take a name, and we can name this port, for example, just ground. Okay, so this port now has the name ground. Now we actually want to connect this LED, because we're supplying it voltage through the microcontroller. We want to then go through the LED, or rather, we want to go through the resistor, then we want to go through the LED, and then we want to go to ground. So now what we want to do is we can connect these two. So say we take PA2, we connect that here to the LED, then we connect the LED to the resistor, and then we connect the resistor to something named ground. And then the software is going to ask us, do you actually want to connect this node to ground? And we say yes, that's what we want to do. So now the program knows that this connector over here and this connector over here are actually connected. So we don't need to draw. Yeah, go on. Escape. I just press escape. Yes. So now this LED is connected to the resistor, and then we're connected to ground. But again, why do we have this resistor over here? What is this resistor doing? So we can then go back over here. So imagine we have a pipe. This pipe is just arbitrary. It has some diameter here. We call it X, and then we have some flow of water going through here. Now this pipe, in theory, doesn't have any resistance. It doesn't have anything that tells the water, in this case, doesn't have anything that tells the water you can only go this much. There's only this much flow that can go on. This can cause a problem. So if we connect this pipe, let's say, to a mill, let's say if we connect it to a mill, and the mill has some, it rotates and it turns. If we don't restrict the flow of the water going through here, this mill is going to turn like endless, like the speed of the mill is going to be infinite, which doesn't work in reality. So the resistor, which we connotate as so, the resistor we place to actually restrict the flow of the flow of electricity or of electrons. So in this case, the pipe, the diameter of the pipe, the potential of water flowing is a voltage. That's how much we can have electricity go through here. There is a current that goes, the current is dependent on the voltage as such. That is, power is dependent on both voltage and current, but current is only dependent, the flow of current, the flow of electricity through the pipe is only dependent on the resistance of the system. So in our case, we have a LED that we want to conduct current through. So if we don't have any resistance of the electrons, we have an infinite amount of current that goes through the LED, and the LED can only handle so much current, right? So we can only we only have a certain amount of current that we can conduct through an LED for it to actually work as the way we intend it to. So that's why we have a resistor here that is connected to the LED. Now we want to connect the FTDI cable over here, and I can never have this memorized, so it's nice for me just to be able to go to the board here, find the board, and I know that the RX is connected to PB2 and TX is connected to RB3. So TB2 and RB3. On our board in the eco schematic, we can find God damn it. Okay. PB2 and RB3. So sometimes. Yes, sir. Okay. Seven. Sometimes there's a difference because this doesn't necessarily represent the Arduino version of it. This is not necessarily what you would. So that's sometimes the difference. You have two here, you have three here, but then you have PA5 and PA6, for example. So PB3 and PB2 are not necessarily the ones that you have in the schematic over here, which is the shame. Okay, I'm going to stop the recording now. Take a 2-minute break, and then we do the rest. We do the schematic design, then we go into the board design, and then finally I'm going to do an Inkscape preparation for the mill.